This video discusses taking field measurements. When we collect measurements, what we're doing is we're recording values. And there are two different types of values that we can record. We can record scalar values, which only have a magnitude, they don't have a direction. Or we could record vector values, which have a magnitude and a direction. For example, 20 miles is a scalar value. 20 miles north is a vector value. 20 miles north and 20 miles south, there's a big difference. There can also be a big difference when 1/8 of an inch means a piece of glass fits or doesn't fit. The type of work that we're doing and the level of precision that it requires have a lot to do with determining how and which measurements are taken. Can we assume the values of the angles between our measurements of width and height are 90 degrees, or do we actually need to measure that? When we don't actually need to measure that, we assume that the measurements we're taking perfectly correspond to plumb and level reference lines, and we call that square dimensions. And so when do we take square dimension measurements? Square dimensions are taken when the allowance is greater than the tolerance. Using a window as an example, the allowance is the space between the window and the opening, and the tolerance refers to the precision with which the opening itself is constructed. In the case of a storefront, we have a 3/8 allowance at the top, a 1/4 inch allowance at the bottom, and this gives us a 5/8 inch allowance in the vertical dimension. At the left and right sides, we have 3/8 of an inch, which gives us an allowance for the width of 3/4 of an inch. The construction tolerance for masonry allows the masonry material to be placed up to a 1/4 inch out of plumb or level in 10 feet. In our example, that means that a total 1/2 inch tolerance is allowable in the width of the opening. So the top can measure a 1/2 inch different than the bottom. And that amount of variation is within the allowable tolerance for masonry construction. Continuing with this example, our masonry tolerance allows a 1/2 inch in the height and a 1/2 inch in the width. Our storefront allows 5/8 in the height, which is greater than the 1/2 inch tolerance for the masonry opening, and it allows 3/4 of an inch in the width, which is also greater than the width tolerance for masonry, which is only a 1/2 inch. Because our allowances are greater than the tolerances, we can take square dimensions. You can refer to our video on construction tolerances for a review of the tolerances associated with different types of construction materials. If you watched the video on construction tolerances, then you might be wondering, what about errors? We've only talked about allowances and tolerances. What about manufacturing or measuring errors? We account for the occurrences of these types of errors in the allowance. For example, the storefront frame size allowance is based on a 1/2 inch variation in masonry, a 1/16 of an inch tolerance for the cut size of metal, and 3/64 of an inch of measurement error. That's just a little bit less than a 1/16. All of these things combine to provide us with a 5/8 inch allowance for the height of the storefront frames, no less. And if you watch that video, you'll know that the occurrences of these errors are associated with probabilities. Probabilities that the metal is going to be cut too large and that the measurement's going to be too small. And we end up with a compounding of errors that creates a situation where the work doesn't fit as it was intended. We're trying to manage the probabilities of occurrence, and we set an allowance based on an expected probability of success. You might watch the construction tolerances video if you haven't already. When we collect square dimensions, we address the potential for errors in the way that we collect our dimensions. So how do we collect square dimensions? We're going to start by measuring the width at the bottom, the middle, and then the top. We're going to record the smallest of these dimensions. It's important that we use the smallest dimension because we know that we're likely to have some amount of error in the size of the materials that will be placed into the opening. And to prevent a collision of those materials, to make sure that they fit, we want to use the smallest dimension. And we're going to do the same thing for the height. We're going to measure at the left, the middle, and the right. Now, if you have a very long opening, then you're going to take multiple measurements throughout the middle section of that opening. But we're again going to use the smallest of these dimensions. And you want to make sure to get multiple dimensions along the length of the opening because the height has a tendency to be smaller in the middle. A lot of times we'll find that openings have a slight sag because the construction materials are bending under their own weight. And finally, we're going to record our dimensions. And we record them in width-height combinations. The width is going to be separated from the height with an X, and the width comes before height. It's reverse alphabetical order. But we always want to report the width before the height. When you look at square dimensions, you can know that the first value is the width and the second value is the height. When we talk about out of square dimensions, we're talking about dimensions that are being recorded where we don't assume that the angle between them is 90 degrees. Showers, angled walls, this sort of thing. We need to record both magnitude and direction. So when do we take out of square dimensions? Out of square dimensions are taken when the allowance is equal to the tolerance required. And in the case of the storefront, we're deducting enough space so that we don't really have to worry about the masonry interfering with the placement of a window in the opening. On the other hand, frameless showers provide an example where the tolerance is equal to the allowance. Frameless showers don't have a frame at the edge of the glass. You see the edge of the glass, and you want to see that edge of the glass nice and close to the tile. That means it should be parallel to the tile. Nobody wants a big gap that's crooked at the edge of their shower. Who's going to pay for that? The tolerance for cut size 3/8 and 1/2 inch thick tempered glass is plus or minus 1/8 of an inch. That means when we order a size of glass in that thickness, what we're going to receive should be within 1/8 of an inch of the size that we order. Interestingly, the tolerance of the glass size is what causes us to have a 1/8 inch allowance between the glass and the tile. We can't allow any less space than that and expect for our measurements in showers to work out for us. Tolerance and allowance are what allows us to set quality standards for different kinds of work. In the case of showers, we're allowing 1/8 of an inch between the tile and the glass. If the glass happens to be cut 1/8 of an inch smaller than the size that we order, then we would have a 1/4 inch gap between the tile and the glass. If we measured a 1/16 of an inch too small in the dimension and a 1/16 inch measurement error is acceptable, then those things would combine to have a resulting 5/16 inch space between the glass and the tile. And that's acceptable. It's not acceptable to have a larger space than that, but it's acceptable to have a 5/16 space between the glass and the tile. That's what industry standards are for. They're to allow us a standard for the quality of the work that's reasonable in consideration of the allowances and the tolerances afforded to that type of work. So how do we collect out of square dimensions? Before we get started, you might refer to the layout video for a detailed explanation of plumb and level reference lines. We're going to have to measure to reference lines in order to collect out of square dimensions. And maybe this is a good place to point out that we're always measuring to reference lines. When you're collecting square dimensions and you record the width, aren't we recording a dimension that's in perfect correspondence to the horizontal plane? And when we record the height, aren't we recording a dimension that's perfectly perpendicular to the width? We're always taking measurements that are relative to reference lines, even though we might not think about it that way. And when we collect out of square dimensions, really what we're doing is we're not going to just assume that all of our dimensions correspond perfectly with plumb and level reference lines. We're going to actually measure the divergence from those reference lines in addition to the measurements of the thing that we're measuring. And that's really how simple it is. We're going to take basically all of the same measurements of the thing that we're measuring, but then we're going to take a second set of measurements that tell us what is the deviation of our measurements relative to plumb and level reference lines. When you need to collect out of square dimensions, you have to approach it with the end result in mind. What is it that you're building? How is it going to be constructed? Where do you want it to finish out? When you are identifying how it's going to lay out, really what you're doing is you're establishing endpoints or points of interest. Establishing those points can be the hardest part sometimes, but once you identify them, all you need to do is collect the measurements between the points, and that's not too bad. I like to start by measuring the distance between those points of interest, same as you would do if you were collecting measurements for a square opening. I don't normally mark out all of the points before I get started though. I like to mark out those points or identify them in the course of collecting all of the measurements. It just seems a little more efficient to me to do it that way. After I collect the distances between the points, I take additional measurements so that I can determine the direction of those distances. Remember, we're not just assuming that those distances perfectly correspond to plumb and level reference lines anymore. We're going to actually measure the distance between these points and reference lines, and we're going to do this with respect to one reference line at a time. A tape measure can only measure one distance at a time, and so we're going to measure the distance with respect to level, and then after that we're going to measure the distance with respect to a perfectly plumb vertical line. By recording the distance and the direction between these points, we'll be able to know the orientation of the points relative to each other. And this concept might be a little bit confusing because I just said I'm going to take measurements that will tell me the direction. And we all know that the shortest distance between 2 points is a straight line. But the universe isn't made up of only 2 points. And in order for directions to be meaningful, we have to take reference lines into consideration. A lot of people get hung up with the idea that these points need to be connected by a line. Of course, any 2 points can be connected with a line. But when we're talking about measuring the relationship to each other, we need to rely on reference lines, and those reference lines can be completely independent from the points that we're measuring. While these points are independent, we can relate them to the reference line by measuring their distance from it. Because we're measuring from the reference line to the point, that means it's not important for our reference line to pass through either of the points. It doesn't have to pass through either one. We just need to know the distance from each point to the reference line. Essentially, what we're doing is we're collecting 2 dimensions in relation to each of the points that we're measuring. We have the distance between the points, and then separately, and with respect to each of the points, we have a distance from the point to a reference line. The difference in the distance between the points and the reference line, in this example that's b minus a, lets us determine the value c, which is the relative difference between the points in the direction of the reference line. For example, if the reference line is perfectly horizontal, then we would be talking about the difference in the vertical direction, because we're always measuring the shortest distance between the point and the reference line. Now we've measured the distance between the points, and we've measured their distance relative to the same reference line. That gives us 2 dimensions, the distance between the points and c. If we imagine that the 2 distances that we measured are lines, and if we connect them with a third line, then what we have is a triangle. And if you watch the video about layout, then you know we can determine all of the dimensions and angles of a triangle when we know only a few of those values. You also know that the reference line that we chose that's parallel to D is perpendicular to the reference line that we measured along when we determined the value of C. Those plumb and level reference lines are at 90 degrees to each other. And so the angle between sides C and D of the triangle here, that angle is 90 degrees. And that's what allows us to calculate the value of D when we know only the distance between the points and their relative difference to a horizontal level line, the value of C. And because we can determine D from calculation, we don't need to measure the relative distance between the points along that line D. So when we collect these measurements in the field, generally we start by measuring the opening as if we were just collecting square dimensions. We're going to measure the bottom, we're going to measure the top. We're not going to measure the middle here because we're going to check the slopes of the boundaries. We're going to measure the left side, we're going to measure the right side. We're not too concerned with measurements along the length unless the opening is very large. Then we have to watch out for the sagging of the top under its own weight. We're going to place a level at one side of the opening, and that level line is our reference line, and we're going to measure from the substrate to our level reference line. We're going to take note of the dimensions along that line, and that's going to tell us their relative heights. You can see we have different dimensions sometimes, and we can do a little bit of math, and we can find out what's high and what's low, and we could identify the high spot. Now, sometimes Well, a lot of times when we have a very large opening, we're going to find that there's a high spot in the middle of the opening and not just at one side. And when that happens, it's not enough to just report the dimensions that we measure. We also have to include identification of the references we used to take those measurements. For example, up 3/16 of an inch and down a 1/4 inch, that's not very helpful. There's no reference point clearly identified within these measurements here. What we need is we need to clearly identify a reference point. In this case, we're labeling a point that's 44 and 3/16 from the left. We're labeling that point as the high point. And then relative to that, we say a 1/4 inch below high point, 7/16 below high point. That describes the condition of the floor based on the measurements that we took. And we could describe the same thing in a different way by using a different reference point. After we capture our horizontal measurements, we're going to do the same thing in the vertical direction. We're going to use, again, a laser line to shoot a line straight up in correspondence with the plumb direction. And then we're going to measure the relative difference between points and our reference line. Now in this example, there's a 5/16 of an inch difference in the positions of these points relative to the vertical reference line. And we can report that as 5/16 leaning away from the opening at the top, or 5/16 encroaching into the opening at the bottom. Either of those choices is correct, but you're not going to include both because you have to have a reference point. And the reference point can't lean away from itself. Maybe it's also worth pointing out that if we measure the slopes of each of the vertical boundaries of this opening, then we could determine the width of the top dimension of the opening by adding them to the bottom dimension of the opening. If we recorded the width of the bottom accurately, and if we recorded the slopes of the vertical elements of the opening accurately, then those values should add up to give us the dimension at the top of the opening. And if you do all of that, then you would not want to report a dimension for the top of the opening that isn't in perfect correspondence with the dimensions of the bottom and the slopes of the vertical boundaries. We're likely to have some amount of measurement error, and those dimensions might not add up. But you could pull the dimension yourself and see, is it within the allowable tolerance for the accuracy of your measurements. So when we're measuring things in three-dimensional space, it can be kind of tricky when you first start to lay things out. But you have to remember there is, or can be, an imaginary set of reference lines extending from every single point. And these can connect that point to other points. The trick is you have to measure in the plumb and the level orientations. And maybe that's where so many people go wrong with this idea of measuring out of square. We're not trying to connect the points directly to each other. What we're doing is we're connecting the points together by measuring along plumb and level reference lines. And those lines are important because we can only take measurements in one direction at a time. And when we measure the distance between the points, and then we measure the relative locations to the same reference line, that ties the locations of those points into this imaginary grid-based system that we can impose on 3D space.